Hello everyone, welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In today's lecture, we would be talking about monolithic microwave integrated circuits. We'll be talking about MICs, microwave integrated circuits. We'll be talking about MMICs, that is monolithic microwave integrated circuits. What are the factors which are responsible for the boost in the MIC technology? What are the advantages of MICs over conventional or the discrete circuits? What are hybrid and monolithic microwave integrated circuits? What are the advantages and disadvantages of MMICs? What are the applications of MMICs? For making MMICs, how do we go for material selection in the case of substrates, conductors, dielectrics, resistors and ferrimagnetic materials. So here we begin with the introduction. With the development of technology for microwave solid state devices, there has been a thrust on miniaturization and integration of devices, circuits, components, etc. in the microwave engineering. This has led to the development of microwave integrated circuits, which have low weight, low volume, are more reliable and insensitive to mechanical shocks, especially for defense and the space applications. When we talk about MIC, the question is, what are MICs? So MIC is an assembly in a planar geometry that combines different circuit functions through microstrip and strip lines. The integration in the circuit is advanced from small scale integration SSI up to 100 components per chip to medium scale integration MSI for up to 1000 components per chip to a large scale integration, that is LSI, for up to 10 raised to power 5 components per chip, and finally the very large integration VLSI for more than 1 million components per chip. So we have gone for miniaturization, that means the circuits have been reduced in size. Now in the recent times, the integrated circuit has advanced to the ultra large scale integration ULSI stage. We just give an example. A 32-bit microprocessor chip has more than 0.15 into 10 raised to power 6 components. 1 megabit dynamic random SS memory DRAM chip contains more than 2.2 into 10 raised to power 6 components. Now we would like to know what are the factors contributing to the boost in MIC technology. The main factors behind the boost in MIC technology are rapid growth of material processing technology such as epitaxy, ion implantation, sputtering and so on. Development of low noise MOSFETs and power MOSFETs. Development of substrates with desired properties such as silicon, gallium arsenide, gallium nitride having high relative permittivity of the order of 13, that is, they have a very high dielectric constant and have a very low loss tangent. The dielectric constant is as high as 13, while the loss tangent delta is very small, 5 into 10 raised to power minus 4. Growth of CAD techniques par excellence. So we have computer aided design technologies which are very good now. The ability of fabricating various devices, both active and passive, simultaneously using the same process. Example, MOSFETs, Schottky diodes, switches, tank circuits, etc. So we have the same technology to just make all these things. Realization of multi-layer processing. So multi-layers can also be processed in. These are the reasons which have led to the boost of MIC technology. Now the question is, what are the advantages over conventional and discrete circuit? So MICs show improved performance. They have a very high reliability. All components are fabricated simultaneously and there are no soldered joints. Therefore, there is no question of breaking of contact, and therefore they have high reliability. They have improved reproducibility. The size is very small and the weight is also small. Relatively low cost because they are always processed in a very large numbers. Now, hybrid and monolithic microwave integrated circuits. Microwave integrated circuits are usually of the two types: hybrid microwave integrated circuit HMICs, monolithic microwave integrated circuits MMICs. In the hybrid microwave integrated circuits, the transmission lines and the matching networks are realized as microstrip elements on a suitable substrate material. The discrete components like transistor and passive components such as chips, capacitors, inductors, resistors are connected by soldering or wire bound techniques. While in MMICs, all active and passive components and the sections of transmission line are formed on the surface of the semiconductor substrate or into the bulk by same deposition schemes such as ion beam sputtering, ion beam implantation, diffusion, epitaxy or evaporation. So here we would like to know what are the advantages of MMICs. They have small size and weight. They carry potentially lower cost as they are produced in large numbers. They have high reliability as all components are fabricated simultaneously and there are no soldered joints. So they are all being deposited simultaneously with the same technique. They have better reproducibility, giving improved performance, which is very important at high frequencies. Much less parasitic reactance, no bond wires. Then discrete package devices. So MMICs can be made with broader bandwidth as compared to the hybrid circuits. Now the question is, what are the disadvantages of MMICs? So MMICs, they waste large areas of relatively expensive semiconductor substrate for components. The processing steps require very critical tolerance for MMIC, resulting in low yield. So it is difficult to make them. MMICs have higher losses and noise. So a high Q resonator and filters are difficult to implement. There is a possibility of adjustment after fabrication. So in MMICs, there is no possibility of adjustment after fabrication. There is a limited range of values for components such as capacitors and inductors. The small size limits heat dissipation, that is, they have poorer heat sinking. So MMICs cannot be used for circuits requiring more than moderate power levels. Debugging, tuning and trimming of these devices is not possible. This limits their use for moderate power and low Q. So this represents basically the structure of MMIC. There is a ground plane metallization. We have the gallium arsenide FET, implanted resistor, gallium arsenide substrate, thin film, that is resistor thin film here. This is the air bridge, microstrip input line, MIM capacitor, inductor. So these are the different parts which generate MMIC. This figure shows a typical arrangement of structure of monolithic microwave integrated circuit MMIC. Monolithic is derived from a Greek word mono, meaning single, and lithos is stone. So these circuits are built on a single crystal. Now this table, what does it do? This table compares the various properties of HMIC and MMIC. Just look here. The first column will show the specification or the property, then HMIC, and here MMIC. Transmission lines and matching networks are realized as microstrip circuit elements. The discrete components like resistor, capacitors, inductors, transistor are soldered or wire bonded. All the active and passive components of sections of transmission line are formed on the surface or into the bulk of a semiconductor substrate by some deposition technique. Now, number of layers. Gradually, in case of HMIC, there are two layers, one for the transmission line and matching networks and another for discrete components. In the case of MMIC, there are several layers of metal, semiconductor, dielectric, resistive film. These may be one layer for each circuit. Generally, semiconductor gallium arsenide and gallium nitride are recently used. Now let us compare the cost factor. So if I compare the substrate, here it is SiO2, SiO, Al2O3, and in this case gallium arsenide and gallium nitride. When I compare the cost, the labor cost is very high, while here, since they are produced in bulk, therefore the labor cost is relatively small. How much substrate area we utilized? To the maximum, and here the substrate area utilized is less. Debugging, tuning and trimming after design possible, but in the case of MMICs, this is simply not possible. When it comes to the size and weight, in case of HMICs, the weight and size is large, while in case of MMICs, they both are small. The design tool for computer aided design we used, in the case of HMIC we generally use it, and in case of MMIC it's a necessity. Processing steps and intermediate testing. Processing steps not critical, intermediate testing possible. Trimming may meet out circuit tolerances. Circuit tolerances to be met out during circuit design. Design steps are very critical, intermediate testing is not possible. When it comes to the parasitic reactances, in HMIC is very high, while in case of MMIC they are very small. What is the operating bandwidth? A very small or a low bandwidth for HMIC, while for MMIC the bandwidth is relatively large. Reproducibility and reliability. In case of HMIC they have medium range, where it is very high, consistent from one chip to another. Now let us compare the design flexibility. In case of HMIC, these generally use FETs and so have high degree of flexibility, while in case of MMIC, these generally use gallium arsenide MOSFETs, so flexibility is less but is still good. Repairability, yes, and in case of MMIC they cannot be repaired. Now what are the applications of MMICs? MMICs are finding applications in the areas such as civil, space and military. When it comes to the military applications, due to low volume, high unit price, phase array radars, telecom systems, small weapons, surveillance and countermeasures. When it comes to the civil applications, it is due to low volume and high unit price. They are utilized basically in satellite communication, instrumentation, optical communication and supercomputers. Another type of civil applications due to high volume and low unit price is in the case of mobile telephones, automobile radars, direct broadcast satellites, that is DBS televisions. Now basic question that we need to address is, how do we make material selections for fabrications of MIC or MMICs? They require 5 basic class of materials: the substrate material, then it's the conductor material, then it says the dielectric material, the resistive films and the ferromagnetic materials for using ferrite devices. The material selection for MIC involves the evaluation of properties like electrical conductivity, dielectric constant, loss tangent, thermal conductivity, mechanical strength, manufacturing capability and adhesion to the substrate. All these properties are very important as per the application where the material is to be used. Now for the first time we pick up something called substrate material. A substrate of MMIC is a piece of substance on which electronic devices are built. The substrate material should necessarily have following characteristics. What are the characteristics required for the substrate material? It must have a high dielectric strength, 9 or higher, low dissipation factor, that is low loss tangent, uniform thickness and fine surface finish, high purity, high resistivity, high thermal conductivity, high dielectric breakdown strength. Dielectric constant must remain constant over the frequency range of interest and temperature range of interest. Now we have a table here where we are going to compare. What is this table doing? It is comparing the properties of substrate material which would be used for the fabrication. The different materials are alumina, quartz, silicon, gallium arsenide, sapphire, glass and beryllia. All their properties are compared here. In the first column we compare relative permittivity or the dielectric constant. In the second column we are comparing the loss tangent, that is tangent of delta, and that is being measured at high frequency of 10 gigahertz. Dielectric strength measured in kilovolt per centimeter into 10 raised to power 3. Thermal conductance, surface finish and applications in MMIC. Alumina for making microstrip line, quartz for making microstrips, silicon for MMICs, then gallium arsenide for MMICs microstrip, then we have sapphire which is used to make microstrip lumped elements, glass for the lumped elements and beryllia for compound substrate. For MMICs, the substrate must be a semiconductor. The choice of semiconductor depends on the type of active device and frequency range of operation desired. Example, silicon for bipolar transistor and silicon for sapphire for MESFETs can be used up to several gigahertz. Gallium arsenide FETs are used up to 60 gigahertz. Gallium arsenide is used to design low noise amplifiers, high gain amplifiers, broadband amplifiers, mixers, oscillators, phase shifters, switches, etc. Gallium arsenide cannot be used for high power requirement. The material for high power requirement should have high breakdown voltage and high band gap fulfilled by gallium nitride. The table shows comparison of the properties of silicon, gallium arsenide and gallium nitride. So we have the material silicon, gallium arsenide and gallium nitride. Their dielectric constant in this, band gap, breakdown field, mobility, then saturated velocity and thermal conductance. So this table just gives a comparison of the properties of the three materials. Then we have something called conducting material. The conducting materials are used for generating conducting patterns and the ground plane. The desirable properties of the conductor are high conductivity, good adhesion to the substrate, low temperature coefficient of resistance, easily deposited and electroplated, good etchability and solderability. So the table is on the next page, which summarizes the properties of commonly used conducting materials along with their deposition technique. The conductors with good conductivity, that is category A, have poor adhesion of substrate, and relatively poor conductors have good adhesion to the substrate, category B. Then the process is to deposit a thin layer of conductors from category B on the substrate and then deposit over it a layer of conductors from category A. The thickness of the later layer should not exceed 4 to 5 skin depths. so as to confine most of the current and provide low resistivity. The choice of the material depends on compatibility with other materials used in the fabrication. Typical combinations used are chromium gold alloy, chromium copper alloy, chromium copper gold, titanium gold, titanium palladium gold, titanium platinum gold. The frequently used gold top surface is excellent for ultrasonic bonding, but copper requires soldering. Material of category D are used to provide the potential barriers required for the active devices. Aluminum is a good conductor and has fair adhesion to the substrate, so its use does not require intermediate layer of materials from category B. So the table here shows the comparison of properties. We have materials, very good electrical conductors under category A, which have gold, copper, silver and aluminum. This table shows their surface resistivity, normal skin depth, coefficient of thermal expansion, how does it adhere to the substrate, and what is the deposition technique, evaporation and electroplating. When we come to the category B, that is good electrical conductors, we have the materials like chromium, tantalum, and these are the three materials here. When it comes to category C, it is molybdenum, tungsten, and for generating barrier conductors, we have platinum and palladium. So the table gives just the critical properties of the material that would be required to make conductor materials. Now, next in the material category is the dielectric material. Insulating dielectric film is required in MMIC to provide insulation for capacitors, overlying lines and active passive elements and to block DC. That is why we require the dielectric films. The desirable properties of the dielectric material are high dielectric constant compatible to the circuit, low light dielectric loss, that is tangent delta has to be as small as possible so that we have a high quality factor Q, capability to withstand high voltages or high dielectric strength, reproducibility, ability to undergo processing without developing pinholes. So the various dielectric materials SiO2, SiO, Si3, N4, Ta2O5, Al2O3. What is the method of deposition shown here, dielectric strength shown here, then microwaves that they are able to, that is the quality factor that they are able to exhibit, then this column gives the values of the dielectric constant. The commonly used dielectric thin film materials are given in this table. SiO2 film is obtained by growing pyrolytic deposition and densifying by heat treatment to obtain high Q film for capacitors of capacity 0.2 to 0.5 microfarad per square millimeter. Si3N4 and Ta2O5 are frequently used dielectrics with a high dielectric strength of 10 raised to the power 7 volt per meter, and so used in high power microwave integrated circuits. Resistive films. Resistive films are used to provide bias to the networks, attenuations and terminations. The desirable properties for the resistive films are good stability, low temperature coefficient of resistivity, high sheet resistivity around 10 say 1000 ohm per square, good dissipation capability, must be able to dissipate heat as far as possible. The commonly used materials are nickel chromium, chromium SiO, Ti, Cr, and the various properties, that is resistivity, temperature coefficient, their stability and their methods of deposition are given in this table. Evaporated Chrome and tantalum nitride are mostly used materials. The exact temperature coefficient of resistance depends on the film's formation condition. Thick film resistors are used in circuits incorporating chip components. Thick film refers to the process, not to the thickness of the film. It refers to the process. The film thickness is taken to be more than a skin depth to have better dissipation. Ferrimagnetic material for MICs. Many times MICs require fabrication of non-reciprocal ferrite devices like circulators, frequently used with negative resistance devices, isolators, switches. Then the material must have following desirable properties: high dielectric constant, low loss tangent to the order of 10 raised to power minus 4, high saturation magnetization, appropriate resonance line width. Mg, Mn, nickel and zinc are suitable for resonant devices. YIG is more frequently used. The two processes in use are a ferrite disc or plug-in cemented into ferrimagnetic substrate. Using ferrimagnetic substance to implement the ferrite components, the devices are magnetized by the miniature permanent magnets. So the most commonly used materials with their properties are just summarized in this table: YIG aluminum, YIG gadolinium, then Mg, Nm, Ni zinc, Al2O3, then their respective dielectric constants given here, loss tangents into 10 raised to power minus 4 given here, saturation magnetization is given, resonant line width is given. So these are the different properties that are desirable for the various type of selection of materials. Hope that you have been able to follow MMICs, their material selection in detail very clearly. Hope our earlier videos have been very useful. Once again, if you are enjoying the physics with us, then you are required to subscribe our channel Physics with Dr. Sanjay Bhargava, then like and comment on the various videos that you are able to see on this channel. Thank you very much. See you in the next video. Thank you.